This event is being broadcast and live and recorded on YouTube. By remaining in this venue, participants acknowledge and agree to the capture and use of their image and voice in the broadcast and recording of this event. Okay?
So this is both an introduction to two fundamental cooperative game theory solutions called the Shapley value and the nucleolus. Yeah. Now, how to measure the individual contribution of participants in a coalitional venture? Game theory, offers two single-point solution concepts. They are the Shapley value and the nucleolus. I start with a simple example to introduce this. See, in our house, we have to mow the lawn every week. We have a lawnmower, and my next door neighbor is very particular that I mow the lawn every week. So the one way of tempting us is to offer a strawberry cake made into 24 equal pieces. He knows that all of us love strawberry cake. The guy on the left side is myself with a lawnmower. The middle one is my daughter Deepa. The right one, which has nothing to do with my wife, it's my wife, you can assume it, okay? Now what happens is, I am the only one who can start the engine for the lawnmower. They don't have the strength for that, but now I have also lost that strength. Anyway, and then on my own, with nobody's help, I can mow half of the lawn, okay? And then after that, I am exhausted to mow the entire lawn. I don't have the strength, but I can always start the engine. So my wife says, if you can start the engine, I can even finish the entire lawn with your help. You don't have to do anything. You can, each time you start the engine, I mow the lawn, collect the grass, etc. And in case my daughter is there, she says, Dad, the two of us can finish 3/4 the lawn. I can finish 3/4 the lawn. You don't have to do anything. You start the engine. So that is the game. Okay? That is the game. And we call it a transferable utility game. We all have an equal same amount of interest in the strawberry cake. I don't want the definition. Just a minute. So let's move on. Okay. I have explained all these things there. Then I can write this information as follows. The worth of me as a single person is half, because I can finish half the lawn myself. The worth of me with my wife Usha is 1 unit. That means we can finish the entire lawn. With my daughter, we can finish 3/4 the lawn. That's why V of RD is 0.75. My daughter alone or my wife alone can do nothing. Or even together, they can do nothing, because they cannot start the engine. The three of us can finish the whole lawn, even otherwise. So how do you now evaluate the worth of each one of us? So we have to do this job every week, okay? So sometimes I may come first to the lawn, Sometimes my wife may come, my daughter may come, enter the lawn. So assume that any one of these random order is possible. The first one is myself is coming first, followed by my daughter, then followed by my wife. In another day, it is myself first, my wife next, my daughter next. So there are 1, 2, 3, 4, 5, 6 possibilities. And what Shapley said was, whatever was done earlier and whatever the new person has done after joining, that person takes away the difference. Okay? So the first time when I enter, I have finished half of the lawn, so I take half of the cake myself. Then my daughter enters, so I take half of the cake. The two of us can finish only 3/4 the lawn, so she takes the 1/4. My wife comes, we still have finished only 3/4 the lawn on this first day. So she takes whatever remains. So you have such possibilities, and then you simply take the average for each person in each one of these trials put together. So if it is like this one, TUD, T means myself, U means my wife, D means my daughter. So it is, for example, if they arrived like this, it will be 0.5, 0.50. If it is this, it will be so much. So you can write down each one of these cases. Agree? So for example, let us take this UTD. U means my wife enters. Nothing is done. Then I come. The two of us are able to finish mowing the entire lawn. But when she came, she did nothing, so she gets nothing. But the two of us finished the entire lawn. And what is my portion? My portion is the whole lawn in that sense. So it is 1, 0, 0 like that. So if you write it down for all the 6 cases and take the average, that is called the Shapley value. Okay? That's called the Shapley value, which is quite intuitive, quite a very intuitive approach to the problem. Okay? He comes directly with a solution and says, this has many remarkable mathematical properties. So those properties are called, say, symmetry, efficiency, dummy, linearity. So I just give simple, give one of the examples, one of them, a dummy. Who is a dummy? A person's contribution, additional contribution or marginal contribution is 0 no matter which coalition the person joins. Then such a person is called a dummy. So according to Shapley's axiom, that person deserves nothing. Now, efficiency, for example. This means when the whole lawn is mowed, so it must be split. The rewards must be split such that there is no wastage. There is nothing throwing out. So the whole 1 unit is used completely. Something like that. So symmetry, axiom, etc. So that's part of Shapley value. And these axioms are imposed on all games with the same set of players. The same set of players can play different games. V of n. We get, in this example, it turns out that I get 19 pieces. My wife gets 4 pieces. I get 1 piece. Okay. So this is the same thing which I was picture-wise I said for n players. I wrote T, I should have written S. What it means is, if a person enters as the est person, or teeth person, let's say. Before the person, there are T minus 1 people. Okay? And after that person, there are N minus T people. Okay? So they could have arranged themselves in any form. In all such cases, that what is the contribution of teeth person? It doesn't matter how the other people came. Finally, T minus 1 people have come. Okay? Those specific people. So you can arrange them in T minus 1 factorial ways, the others in N minus T factorial ways out of N factorial ways. So that's the kind of expected marginal contribution. This is the marginal contribution of the ith player when instead of S, you think of some capital T or whatever it is. The marginal contribution multiplied by this probability and summed over all these cases. So that is the Shapley value. Okay. Now there is Shapley. See, the early stages of game theory, the cooperative game theory, were studied first by von Neumann. He introduced the concept with von Neumann and Morgenstern, and they were always trying to find something else, what is called a stable set, which is a slightly more complex thing. And over the years, it was the entire game theory gang was spending their life and fortune on finding stable sets for various games. And Bill Lucas came with a 10% game which didn't have any stable set. So the concept of you see, any idea, if it is too difficult to solve, and at the same time it is not universally true, it loses its importance. So the stable sets lost their importance, even though people had spent fortune of their time. But then Shapley, and even before Shapley, I am not remember the name of the other person, they both introduced the concept of a core. So what is a core? Suppose if you are given, you have say 3%, x1, a, b, c. A is given x1, b is given x2, c is given x3. The total is the total worth of the volume. Now, x1 should be at least as much as what that person A can do on one's own, the worth of him. X2 is similarly for second, x3. So I want x1, x2, x3 satisfy what is called individual rationality. The second thing is, if you add x1 and x2, that should give at least as much as what the two people can get by their coalition. So you have a set of linear inequalities. So in n-person game, you will have x1, x2, xn, sum of xi over all I over a set S. Each set S is called a coalition, is at least what they can get on their own as a coalition. So that's the notion of a core. So the core suddenly became a more meaningful definition. Not that it also exists, the core may not exist. For a game, the core may not exist. Yet, if there are two things which do not exist, one of them is a lot more intuitive, that dominates. Ultimately, that dominates. Every subject has the same situation. In statistics, early days, you collect data. Only two things which you can calculate is, for example, the average. Another thing is the median, central value. There are any number of such things which you can cook up. But these two have more and more mathematical properties, so they stay. So in the same way, Shapley value stays because it is elegant, it's axiomatic, and at the same time, for a wide class of problems also you can compute it even in field. But it is not in general easy to compute even for certain simple classes of games. While it may be easier for some other class, but for some simple classes, it's not easy. But the core is something which one can guess. So here is what is called a harsh market. There are 6 sellers and 5 buyers. The 6 sellers, they want to sell all the horses are identical. From the buyer's point of view, they are all identical. They look identical. There's nothing special about them. Only thing is, people have their own greed at what price they want to sell. So seller one expects to sell at a price at least 30. He doesn't want to part with his horse if it is more than 30, less than 30. Like that, I have written for the 6 sellers and 5 buyers. But only thing which you can intuitively feel is all horses should have the same worth P. Okay? So there is a price P. There is a price P. If you fix that price in the market and look for how many sellers are there and how many buyers are there. Suppose I fix the price P as 39. For the price P 39, you have 1, 2, 3, 4, 5 sellers are willing to sell because all of them want at least 39. So these are the 5 people. But how many will be willing to pay 39? Only 1, 2, 3. So the number of buyers, number of sellers, namely the supply, is more than the demand. Agree? The demand is only 3. So the price is too much. So the price has to come down. So there is some price at which the sellers and buyers numbers are same. So that's the so-called equilibrium price. And in that sense, that price also is a price in the core price. Every equilibrium price is a core price. Okay. So horses look identical. The price P at which demand equals supply satisfies this condition. So it can be any price between 37 and 38. Less than 38, at least 37. Okay. So a distribution X is in the core if and only if XS is at least VS for all coalitions S. In the case of lawn mowing, the Shapley value which I computed as 3/4, 1/4, no, it is not the Shapley value. It is some value. 3/4 for me, 1/4 for my wife, 0 for my daughter. It is in the core. The entire thing comes to me is also in the core. However, the Shapley value which we computed is not in the core. See that what Shapley value offers. "19 out of 24 for me, 4 out of 24 for my wife, but the 2 of us can finish the whole lawn, so we should get 1. Okay? We are not offered 1 in total. So the Shapley value itself is not in the core. Okay? So now if you want to respect core more than a particular value, you look for something else. Is there something which is individually rational and which is in the core if the core is non-empty? Okay? And which is in some sense unique. So a unique element X in the core, which is the best for all least happy coalitions in the game. See, imagine the following situation. The society is split into n different types. Doctors, lawyers, professors, etc., etc., etc. And some workers, etc. Now, for each set of coalition, Suppose if x1, x2, xn is offered for these people, and I want to compare two possible imputations. That means these are individually rational and the total is the worth of the grand coalition. So I offer x and I offer y. Between the two, which one is better? So you have to, in some unique way, you have to say that. So what you do is, you evaluate the satisfaction when x is offered for each coalition. So it is x of s, which is summation xi I over s. And Vs is the worth of the coalition. So this difference, if it is positive, they are satisfied. If it is negative, they are unhappy. Okay? So even if everybody is satisfied, there will be one which is least satisfied. So the way you compare x and y is, which one is better of the two in terms of least satisfied group. If the least satisfied group in x is better than the least satisfied group in y, then I like x more than y. The government should choose x over y in some sense. So if these two are equal, you move to the next least satisfied, the second least satisfied. So you proceed like this one, and then you can evaluate one of them is strictly better than the other one. So this process tells you there should be one which is the best among all. And Schmeidler was the person who defined it in 1969 and proved that there is a unique element. Okay? And it remained dormant for a while. And computing the nucleolus, such a solution concept, has always been a very difficult problem, which is involving linear programming in several stages, and it can be hopeless. In general, to solve the nucleolus is as hopeless as in general to solve Shapley value, in general. However, there are some practical class of games for which Shapley value is hopeless, but nucleolus is the best. Okay? So I want to first talk about one such class. These are called assignment games. Players are partitioned into two groups. Payoffs are defined for each pair consisting of one player from one group and one from the other group. You can think of either sellers and buyers, or you can think of girls and boys. Okay? Anything. For pairs contained in the same group, there is nothing. In the traditional sense, we will not allow pairs from the same group to have anything. Okay? For larger coalitions, the payoff is the total value from the maximum matching among the coalitions. They are traditionally represented as a matrix, where the two groups are represented as the rows and columns. For all assignment games, a set of imputations exists for which the satisfaction is non-negative for all coalitions. So, can we compute the nucleolus in polynomial time for this special class? This is what we did in 1994 with one of my former students, 1994. Generally, for those games, it is quite NP hard by Shapley value. So let us start with a simple example. There are two house owners, house owner 1 and house owner 2. Owner 1 is expecting at least 200 for his house. The second guy expects at least 230. There are two buyers. Buyer 1 values the first house worth 290 at most, and house 2 is worth at most 260. Buyer 2 values at most 300 for first house and 280 for second house. He is always overestimating. Okay. Now, these two people, the house owners and the buyers, they approach a common real estate agent. That real estate agent keeps who is the seller and who is the buyer secret. All he does is he shows the house to the buyers and then gets the information what is the level maximum they are willing to pay in case the owner is willing to sell. And similarly, what is the price at which house owner one will part with the house, with somebody if he can find a client. Now, the strategy of the real estate agent is to get commission from either from both sides or from one side. Okay? It could be from the commission which he gets. If suppose he sells it at a price P, which is more than 200. So house owner 1, suppose he is willing to sell at that price, so he gets P minus 200 as the gain for house owner 1. So a proportion of that must be given to the real estate agent. So in the same way, you can write down all of them. So the real estate agent ultimately kind of basically trying to sell house 1 to B1 and house 2 to B2. Because the gain here is 90 plus 50, 140, but other way it will be less than 140. Agreed? So that's the way he will do it. So the coalition gain matrix is 90, 100, 20, 50. So seller 1, 90, seller 2, 50, buyer 1. So the real estate agent is collecting proportional to 90 and proportional to 50 from sellers 1 and 2 as his service charge. From buyer 1 and buyer 2, he doesn't collect anything. So when you look at it, he feels, the seller 1 feels that he is paying through the nose for the entire thing. He could have sold it to the second thing. He could have sold it to a higher price. Let me put it this way. To deal between 200 and 300, if he had put together, he would have gained a little more. Okay, so he feels somewhat unhappy. And this matrix helps you to build up a graph. And through the graph, you are able to reallocate. Namely, you find a better imputation than the current imputation. So each time it is trying to improve the imputations. That's what and in the end, it ends with the nucleolus. So that means you have to have a certain graph theoretic connection, and it goes on and on, many things. First time it happens to be like 90, first it was 90-50, now it is 90-40-0-10. That means the second house seller, he doesn't pay 50, but he pays only 40. He wants the buyer 2 to pay 10 as commission to the real estate agent. So it continues. in different stages, but it has to do with manipulation with this graph. And it has to find at each vertex, the longest path ending in that vertex. And that's the whole thing, and it's a long theory, okay? And several steps are needed there. The whole problem was, while this was done, it was over, and we tried to show that it is polynomial in time, efficient as an algorithm. But I was trying to appreciate what is going on in society, in the marriage market. So, what is a marriage market? You have n girls and n boys. Each girl, you can think of the boys as the rows and girls as the column. The boys as the rows and girls as column. If the boy and the girl, they like each other, then in that entry, ith boy likes the jth girl and vice versa, then you put an entry 1 in that place. If the boy or the girl, if the ith boy or the jth girl, they don't like each other, even it can be one side may be liking but not the other side, then you put a 0. So I get a 0, 1 matrix. I get a 0, 1 matrix. Okay, let me. Okay. So 3 boys, A, B, C, and girls D, E, and F. Compatible pairs are AD, AE, BE, BF, CF. Now I want to close this one. I need the help of Brian. Can you see? I want to close this.
Yeah, and open the other one. Yeah.
Okay. I close.
Hardware.
Just close
yeah.
this. Yeah.
You want this
And
one?
plus, click it. Let's see what happened. What it?
Yeah.
No, not this.
No?
Go further down. Next
2,
one.
3.
No, this is fine. Okay.
Okay.
Okay. Okay. So the compatible matrix is A likes D and D likes A likes E and E likes A, and A doesn't like F, or F doesn't like A, one of the two. Therefore, it is 0. So now it is given. Okay. Now this matrix is given. Certainly A and D can be married because they both like each other. B and E can be married. C and F can be married. This is the maximum marriage because all the 3 got married. The whole question now is, in these marriages, who are the dominating persons? In the marriage between A and D, between the two, if you think of this 1 unit of power as split between the two, that is 1 unit of power has to be shared. If somebody gets a higher share, that person is the dominating person. Okay? So, my question is therefore to treat this as a cooperative game and look for its nucleolus as a measure of that. Okay? As a measure of the dominating power. So, in this case, one can show that the nucleolus satisfies A gets 3/4 and D gets 1/4. Does it make sense intuitively? Why do I say that A is the dominating person in the marriage of A and D, one intuitive understanding is, look at D. The girl D, she likes only A. And she doesn't like B or B doesn't like D. That's why it is 0. Either she doesn't like C or C doesn't like D. That's why it is 0. So her only liking is for this boy A. Okay? Otherwise, she has to remain single. If it is a marriage which she agrees to get married, she should be ready to accept a stronger power from A, simply because if she ever creates some problem with A can tell, I'm going to leave you. I'm going to try E. I'm going to, even though E is married to B, I'm going to lure her. Okay? We both like each other. I may spend more money than her husband and some things like that. And therefore, the power of A is more than the power of D. The same way, if you look at C and F, C gets 1/4 and F gets 3/4 in the nucleolus. Because C, this boy C is liked only by the girl F. The others rejected. So when you analyze it, F has more power, and that's what it is. But if I look at the split of this domination, instead of domination power, if I took Shapley value, and then the Shapley value is written underneath it. 36/60, 31/60, blah, blah, blah. These numbers purely are mathematical. They are not truly intuitive. I don't see anything intuitive about them. Okay? In some sense. So the question is, in the case of assignment games, we have to deal with, on the one hand, we have to deal with a graph which is constantly growing and shrinking. And at the same time, slowly it is shrinking and finally comes to a single point. And at each iteration, you have to also manage the matrices which can have different numbers. Here, the matrix, if you manipulate, the next matrix is either one of the 1 and 0 kind only. So nothing is changed. So there is no need to work with the matrix. You need to work only with the graph part of the problem. Okay? Now I go to the can you I have to put them there.
Oh, this is paper.
Huh? No, this one is the paper, but page 23.
Was it good? Okay.
Yeah, that's good enough. So let us think of the following marriage market consisting of 7 boys and 7 girls represented by this matrix. The boys are the rows and the girls are the columns. Okay? So the boy 1 likes girl 1, boy 2 likes girl 2, boy 7 likes girl 7. Along the diagonal you have 1. So in theory, they can be married. Now we want to know, given this, what is the power? Relative power. Namely, the nucleolus. So given this one, the strategy of computing this, I only want to give the algorithm. I only want to give the algorithm. Next page is. Okay. What you do is, you associate a vertex with each player. You associate a vertex with each player. So for player 1, it's a vertex. And then you think of player 1 as boy 1. Boy 1 is also interested in the wife of boy 2. The boy 1 is, even though they were married like this, boy 1 has an interest with this wife as well as with the second one, with girl 2. So if boy 1 is interested in girl 2, I connect it with an edge, a directed edge. And boy 2 is interested in girl 3. Okay? So you are connecting with another edge. Similarly, boy 4 is interested in girl 5. Boy 5 is interested in girl 6, and boy 6 is interested in girl 7. Once this graph is constructed, the next step is to introduce 2 dummy vertices. This is boy 0 and girl 8. Boy 0 means is all in all, most dominating. Girl 8 is the most dominating girl. These are 2 dummy boy and dummy girl. Every dummy boy has to be connected if there is no connection to somebody. For example, 0 must be connected with 1 because it's not connected with somebody. Okay? Going in towards that person. So similarly, you can fill up everything for the girls also. Once you do this one, all you now try to do is find the longest path starting from 0 and ending in 8. So you have to find first the longest path. So this is an algorithm separately by Noltmeier to find the longest path. Okay. So the first one, you start with 1, 2, 3, etc. You introduce this one in the second graph. In the third graph, you now notice the longest path from 0 to 8 is 0, 4, 1, 2, 3, 8, suppose. You have found that. 0, 4, 1, 2, 3, 8. So 1, 2, 3, 4, 5. There are 5 edges from the start to the end. So they all share 1/5. Each one is losing 1/5 of the power. 1/5 of the power they are losing. And for example, for 0 there is 0/5 of the power. But for 4, he loses 1/5 of the power. So the fourth person's power is not whole 1, but 1 minus 1/5. And then for the first person, his power is losing 1, 2. 1 minus 2/5. For the second person, 1 minus 3/5. For the third person, 1 minus 4/5. For this eighth person, which is a dummy boy, 1 minus 5/5. So that's how you do. and you collapse cycles, so which means you cannot change their power anymore. If you go along the longest path and fix these numbers, these are permanently fixed for them. Okay? Once you have done that one, there will be others who are not fixed. Now, again, we set W values decreasing uniformly along the path. Now, when you look at it, let's look at the picture again. 1 minute. I don't know how to. Okay. See, 4 was 4/5. And now all these people have been fixed. 0, 4, 1, 2, 3, 8 have been fixed. But the others who are not fixed are 4 to 5, 5 to 6, 7, and 6, 7 to 8. So you have 1, 2, 3. There are 3 edges. So this fellow's power is 4/5. This, it is 0. So the difference is 4/5, which is to be divided equally among 1, 2, 3. Okay? So it is 4/15, and that way you subtract. Oh.
Press down, right?
That, I'm trusting wrongly.
I know, it's just.
I see. Oh, okay.
Yeah,
Oh,
that
that should
should.
do.
You
Okay.
can go press.
I wish. Okay.
Oh, you have to have. Oh, no. Some. Okay. Yeah, I think you can, let's close that. You don't want that. Okay.
Yeah, come down. Can you come down?
Yeah, sure.
Okay.
You're good.
Okay. So now you see, this is the actual nucleolus. The actual nucleolus is 3/5, 2/5, 1/5, 4/5, 8/15, blah, blah, blah. So this is the algorithm which I was hoping to find on my own, which I couldn't do, which I suggested to the student to work on this problem. And he did a very beautiful way, the whole thing. And on top of that, I have to also mention that in our claim, we claimed that in our older algorithm on assignment games, the order of the polynomial is such and such. And he constructed a counterexample to what we claimed and said the order must be one more. Instead of 5, it should be 6, 6, something like that. Okay, and that is, I really thought he was very, very, very sharp on that. Okay. And then this, I said, it is not enough that you talk to me, you should openly defend at the thesis committee. You should point out where we are wrong. It is important. Okay. In a sense, we have a Vedic sentence, like whatever I said. Sahana bhavatu, sahano bhunaktu, saha virjam karavavahai, tejasvinavaditamastu ma vidvishavahai. Om Shanti Shanti Shanti. I am a teacher. I am searching for good students all over. Please, good students, you come and spend the time with me. It is not that I am also going to teach everything for you. I am also going to learn something from you. The teacher also will be learning something from you. Let us work together. So that was the spirit with which the old people were saying, and that was something sitting, and then I want to tell him. So that's what happened. And the algorithm, he not only solves this case, the second case is, which is the most familiar, the new emerging society, where why should man marry a woman? Why not man and man live together? Why not woman and woman live together? Whatever is that society, okay, in the same-sex marriage, that means you have to consider each individual separately as a point. You connect two individuals. It can be a man and a woman, or it can be a man and man, and you draw a graph with an arc length which depends on the level of satisfaction they have between these two. So you can fill up a graph like this one, and then in this graph, you want to find the maximal matching on this graph, okay, by Edmond's algorithm and whatnot. And it has something to do with pendant vertex, everything. It goes through a lot of graph theory before you can really find out the nucleolus. That's what he did in the second half of the thesis. And I also have to tell one more last story. The story is, I said, because you want to work in cooperative game theory, if you want to work in this, you must be quite strong in graph theory. So take a course in graph theory and master it before you come to cooperative game theory. That's what he was taking a course with somebody, and that professor thought he's going to work with him in graph theory. But ultimately, no, I came to learn graph theory to work on a game theory problem. So that's what happened. Okay. So anyway, to cut it short, that is a nice thesis. Okay. And I can send, I'm giving a copy to Merilda so that anybody who wants it can get it, because I don't know the people. Okay. So that's the introduction to nucleolus. I stop here. That's enough. Okay. Thank you. If you have any question, you can interrogate me in every sense. Yeah.
One interpretation of your presentation today that you voted for nucleolus in favor of Shapley value on the basis of computational complexity.
Yes. For special classes. It is not going to be valid for every case.
I understand.
Yes.
But let us take the assignment game where you demonstrated that nucleolus is easy to compute.
Yes.
But let us worship the Shapley value. So if we wanted to try to find algorithms that approximated the Shapley value on that class of games, how would we frame this question? What would it mean to be close to the Shapley value, and how, what?
I still, even for example, I still do not know when is even the Shapley value and the nucleolus are same. Which class? I don't know. Both are unique. Sometimes, as a graduate student, I tell you a simple example. As a graduate student, if you take a matrix with all entries positive, a square matrix, then its value is positive anyway. Okay? It's a payoff matrix. It's positive. If you have a positive matrix, it has a unique positive eigenvalue. This value is unique, eigenvalue is unique. If I know this, can I express the other one as a function of this? No, I don't know. So I was struggling, and finally, a beautiful paper by Blackwell illuminated what is going on. So like that, uniqueness, even though they are both unique, I still do not know what is there a way we can somehow recover one from the other? No, I don't know. That's, but in fact, once I was talking to Shapley about this. We prefer nucleolus over your Shapley value because formula is hard to compute. No, the Shapley value. He said, I have given explicit formula. What else you need? I have given you an explicit formula. What else you need? Then I said, Professor, I can only explain it through an analogy. Shapley value formula which you have given is equal to solving linear equations using Cramer's rule. See, if you want to solve Ax is equal to B, and then if you want to, if A is invertible, for example, then X is A inverse B. To write A inverse, you can write it as the ratio of two determinants. Okay? So that's all, that's the kind which you are giving. I am looking for coming to the answer by iterative steps, not in one round, in few rounds, like Gaussian elimination. So the analogy of this algorithm is very much like Gaussian elimination. Whereas the Shapley value computation is too explicit. Okay, I can stop. Yeah.
Yesterday, did many people comment on your cake cutting abilities? Yes. I don't know if you got that joke over and over.
I don't know how. This one is actually working. Okay. All right. So it's time for me to start this last lecture. The history of the result that I'm going to mention has to do with the intersection of computer science, operation research, and mechanism design. So it happened around the 90s, and particular middle 90s, that people in operation research and computer science started to realize the importance of game theory and, the interaction of computers, each following its own algorithm and so forth, which did raise strategic questions. And then a subset of them also looked at the issue of computational complexity. In particular, Papadimitriou Koutsoupias, mid-1995 or something like that, had very nice papers to discuss the complexity of computing Nash equilibrium and discovering that it was actually a difficult task in most contexts. And then concomitant with that, I mean, developing along the same time, there was an increasing interest in various concepts of game theory and of fair division. So by around 2000, the beginning of 2000, a group was formed, a sub-community, which is called ComSoc, or Computational Social Choice, which focused on social choice theory, but social choice theory understood as also including fair division, and contributed some really important results, in particular because they were immediately attracted to problem in which our standard technology using divisible everything and therefore continuity, differentiation, and all these tools are not present. And one, the sort of the paramount topic, I mean, it's not the only one. I mean, they did more than just the fair division of private good, but that's all I'm going to talk about now. What about the division, the allocation, to not have the division of indivisible object, but the allocation of indivisible object when we have just those objects and no ways to eliminate or alleviate the indivisibility. Family heirlooms would be a group of people, of family members who have to share a bunch of objects which come from some inheritance or whatever. And they are not going to say, look, I mean, you will take that table and I will take this nice painting, but you need to pay me so many euros because, of the market value of these objects. So effectively, by the media of transaction, of monetary compensations, you end up restoring some large degree of divisibility. So there is nothing of that going on, and still we would like to have systematic solutions and methods. So of course this is very plausible in the context of the internet, where a lot of the transactions that happens are not monetized, because monetizing them requires a much higher degree of security and so forth. So, all right, so here is going to be the model. Here's going to be the model, very much like before, but much simpler in a sense on first glance. I mean, a set of objects, M is the number of objects, N the number of agents. As before, as in the K-cutting and allocation, is a partition. And the utility functions are additive, which makes for a very simple representation and also easy to implement, easy to elicit in context of experiments and actual mechanism. But as before, I mean, there will be no intercomparison of utilities of the sort, you have a bigger gain of utility than I have going from this to that allocation. This sort of thing will not enter. What you will only have is the flexibility of the additive components. I mean, of course, the theory also develops for many other classes of utility functions. The most advanced being the one in which there are essentially no restrictions on the way you assign a utility level to any subset of the object, or maybe a minimal monotonicity assumptions. Things become much more difficult, and but the spirit is the same. So by just looking at additivity, we will have a good sense. I think I can give a good sense of what's going on in this very, it's probably the most vibrant subset of the literature these days compared to the other lessons I was covering, the other topics I was covering. Okay, so we start with fair share. We follow exactly the same agenda: fair share, envy freeness, competitive equilibrium here can enter, but has not been very successful so far. So you will see. I mean, it will enter at some point. Okay, fair share. So we know that in the cake context, the natural fair share is 1/n of my utility for the whole cake, right? So it's natural to think of that one. And it's also natural to immediately realize that because of the indivisibilities, it is not possible typically to achieve 1/n of utility for all the objects for everybody. And of course, the standard example is when one object is very valuable for everybody and the others are essentially worthless, then you are hitting the maximal problem of indivisibility. So one way around that, which was initially proposed by an economist, actually, Eric Budish, I mean, an important figure in mechanism design, was to say, look, I mean, we're going to use the same sort of ideas as we were talking about in cake cutting yesterday, which is this idea of, you know, the best partition in which the level of utility I could achieve by choosing the partition myself, but then being in the position of the last chooser, or symmetrically not choosing, being offered a partition which could be as bad as possible, but then being in the position of the first chooser. So those are the max-min utility and min-max utility. And if you look at this inequality, you see that actually they go in exactly the opposite way as they were yesterday with the cake with continuous utilities. With the cake with continuous utility, we had that the min-max was less than the max-min, right? We didn't have that number in the middle, but that was, you know, that was a difficulty coming from the completely different topological nature of the problem. Here, what happens is that the min-max is certainly a level which is not achievable. Because think about it, in the min-max, you are offered a partition of the object in n shares, and you are given the choice, the first choice, but you cannot choose the partition. So you should assume that the partition will be chosen by an adversary. Nevertheless, because your utility is additive over all goods, it is inevitable that at least one of them, one of the shares, is worth to you at least 1/n of your total utility, because your utility for the shares is additive. In total, it gives you UI of A, so one of the shares is worth, okay? So it's completely clear. In fact, if you have additivity and also and also divisible good, you would say that all these three numbers are equal. But here you have this inequality. So min-max, forget about it. I mean, it's absolutely hopeless because it's already hopeless with 1/n. But max-min doesn't look bad. Max-min doesn't look bad because max-min is exactly divide and choose for the case of two agents, right? Your max-min share in the case of two agent is definitely feasible. Because if you are the divider, you will divide the goods in two shares which are as equal as possible to optimize the value of your lowest valuation. So you will be able, as the divider, to obtain your max min. And as the chooser, you will be able to obtain, well, in fact, your min max, and definitely the max min. So there is no question that max min is perfectly fine. In fact, it is the max min for the case of two agents is the natural and maximal fair share. I mean, so this is why Budish was perfectly correct and to suggest that probably max min could work for more than two agents, right? So n equal 2, divide and choose, guarantee max min, very well. And arbitrary if the utilities are identical. It's a very simple thing that the max min is also feasible, because really you just have the unanimity profile. So you just do the division which gives the largest possible share to the smallest share, everybody having the same utilities. And then he said, but what about the general case? It's perfectly, it's a level of utility that we can compute for everybody. Let's do some experiments. People did experiments, numerical experiments, for about 3 years without understanding, yes, it was always feasible. It was always feasible in those experiments to give that level of utility to each participant, but the proof of why it would be systematically true was not coming. And in fact, it was not possible to come because in some very rare and very knife-edge cases, enforcing this max-min level of utility for everybody is not possible. But the cases, I mean, I don't have time to go through that example, but if you care, to look at this initial paper, Procaccia and Wang, who propose a counter-example for n equal 3. So as soon as you have 3 agents, they are able to cook an example where you cannot give the max-min utility level separately to each of the 3 participants. And the example is really the type that cannot come from a numerical experiment, because for instance, the utility of everybody for all the objects is essentially 1 and plus a minuscule amount that varies across agents, so that because the main part of the utility is the same, you end up with an allocation. You must end up in a max-min division with an allocation where everybody gets the same number of objects. And then after that, they run a sort of Sudoku game between the little epsilon. It's very beautiful, but it just shows, they also showed a bit later that those things are very rare. And then it developed, I mean, these people developed very systematic and very extensive, large effort to understand what fraction of this max-min utility you can always guarantee. In the initial paper of Procaccia Wang, I mean, they showed that you can do 2/3, but then it was discovered after much effort, a long literature, that you can do very close to 3/4 and a little bit above 3/4. And also you have an upper bound, so you can enforce at least 3/4, or and in some cases, you cannot give more than 39/40 of your max min. So in other words, the loss sometimes is as high as 1/40. So of course, those kinds of results are very useful and very well appreciated in computer science, less so in economics, because of course they are fine-tuned. I would say personally, I mean, I find those results beautiful, but the thing that bothers me most about the max-min utility level or any of its approximation is that it is a very difficult concept. I mean, checking whether a given allocation passes the test is not a trivial task. I mean, you can, of course, you can compute it if you have a good machine, but if I give you, if I give you 15 objects and some arbitrary utilities to compute your max-min utility, is tough. I mean, it becomes very tough quickly. So that's one thing. There is also the fact that it's not a defined concept. We have not defined the fair share. If we say the fair share is the optimal share of max-min that we could achieve, it's a kind of, I mean, I don't know. I don't like the concept. I think it's just too imprecise. And so in fact, the literature has mostly turned away for this approach to the fair share and took a completely different tack, which turned out to be more fruitful because it will also extend the same sort of approach will extend in the case of the more sophisticated envy-free concept and so forth. Okay, so now we start again, and we don't really look at terms in terms of the, maximal guaranteed level, but implicitly it's still there. We talk about a proportionality which is approximate in the sense of this inequality. So in other words, you are going to call an allocation proportional up to one object if the following hold true for any agent, and when you consider the share of this agent, if it is already above the fair share the average level 1/n of the utility for the whole set, that's fine. And if it is not, you will still restore this inequality provided you are allowed to add one extra object to the share of this agent who happens to receive less than his or her average utility value. Okay? So it's a good concept, of course, if the objects are not too different. I mean, you will not go, in this theory, you will not go away from the fact that if you have one object which is worth everything and the others are worthless, you are not going to get any interesting result. And in fact, you must be in a context for the theory to be interesting where some of these objects are small, some are large, but the range of variation is not too big. Okay, so the new fair share is the smallest corresponding utility you can define in this way. And notice that it's very simple to implement. It's very simple to implement to construct such an allocation. Simply ask each agent to bid a number of goods. Namely, the idea, the message is, okay, we are dividing 12 objects between 3 people. I will be happy with 3 objects. Meaning, if you give me 3 objects, I can choose them properly and I will have my proportional share. So they bid for a number of goods, and one of the smallest bidders get to pick exactly the number of objects that he bid. Okay? And in that way, he gets, you can tell that if he bids optimally, that is, he bids the minimal number of objects that would give him exactly that property to be proportional up to one object, then it's a simple exercise to check that when you do that and then you repeat with the remaining agents and remaining objects the same thing, you enforce that constraint. Okay, but that's just proportionality. We are also interested in envy-freeness, and because this idea of up to one good obviously can be applied in other contexts. I mean, okay, so look at envy freeness. So the standard definition, and now when it is not satisfied, we will be happy if the situation is that people who happen to be envious of some other agent's share could eliminate this envy by mentally, as a thought experiment, eliminating at least eliminating at most one object from the share of the agent that they envy. All right? And notice that in this definition, what happens is that if I is envious of J, I will take this advantage of the definition by taking away from the share of agent J whichever outcome A is the best from the point of view of agent I, right? So agent I has the choice of the object to eliminate. So it's a very strong elimination, because you can kill in the share of the other agent whichever object was for you the most attractive, right? Okay. So it's still a little. There would be something even weaker to ask, which is that, I want to not just eliminate one object from your share, I want to grab it and put it in my share. That would give a condition which is obviously weaker, because that one over there implies this one, of course. I mean, because we are talking of goods. Okay. So that's a second adjustment of the envy-free concept. And just like the previous one, it's easy to implement. Okay? So first of all, we notice that in this theory, because utilities are additive, you have the sort of implications that were there even before, namely that envy-free will imply the proportionality, right? Envy-free implies proportionality, because if I do not envy, let's say that you have three agents. I'm agent 1, and I'm not envious of the share of agent 2, and I'm not envious of the share of agent 3, and I'm not envious of the share of my own share. So now I have three inequalities that tell me that the utility of my share is bigger than the share of agent 2, the share of agent 3, and my own share. I take the average of this utility, and I'm saying that I'm not envious of my average utility over all the objects. So, and you have exactly the same sort of argument with a little bit of work to show that EF1 will imply a proportional 1. Right? So there is the same logical thing. So instead of doing proportional 1, why can't we immediately do EF1? EF1 is easy to achieve because we can do a very well-known mechanism, which in the US is known as NFL draft mechanism, but in general is called sometimes round robin and so forth. I mean, as soon as I describe it, I think you will recognize you fix an arbitrary priority ordering of the agents, and then you let them take turns, agent 1, agent 2, agent 3, then agent 1, 2, 3, etc. And each time they take their turn, they grab one object, which is, of course, for them, the best of the remaining object, of the object not yet taken. Right. And in fact, in this, so to understand why, by doing so, you obtain envy-free up to one object. It's a very simple argument, is to say, okay, so suppose you are someone in this algorithm. If you are the first agent, you are not going to envy anybody. because each time you choose an object, the people who choose their first object, you don't envy them vis-à-vis their first object. But then for the second object you pick, you are also not envious and so forth. But now if you take the point of view of an agent who is not first, it's possible that, for instance, this agent envies the share of some other agent. That other agent must be higher than him in the priority ordering. But so it is enough to take away the object, the first object that agent higher than me in the priority ordering was taking. Because once that object is removed, vis-à-vis that agent, I am in the position of choosing first every time, right? So if again, if I am if we are 1, 2, 3, and I'm agent 3, and I'm envious of agent 1, I take away the first object that agent 1 takes, and after that, comparing me vis-à-vis agent 1, I in fact was taking every time an object before agent 1. Because now his first object is gone. So that's why you get immediately the NV3 up to one object. Okay. Now, clearly you get some inefficiencies with this mechanism, and that is a problem because, of course, we are still very concerned by the efficiency goal. I mean, we are economists, right? So look at a situation like this, A, B, C, D, that is four objects, 2 agents, and they both like A the best. If you let agent 1 start the algorithm and choose first, it's going to get A. Then in the second round, agent 2 will only get B, will get an object value 1. Then the third round, the third pick will be agent 1 taking an object 8. So you will end up here, and then agent 2 gets an object here. So you end up here with the utility 18 for agent 1 and 2 for agent 2. Which is inefficient because it would be much better to give object A to agent 2 and all the small object B, C, D to agent 1 for a total of 24 versus 10. And you can expand the inefficiency as much as you want. So there is a real problem here, is that you don't pay any attention to efficiency, just like we did yesterday when we were doing cake cutting. I mean, we do NV-freeness, but efficiency is not there. So now we want to achieve that, and this is the next step. I mean, after the definition of the concepts, right, we look for an allocation which is NV-free up to one object and Pareto optimal, which means that we will have already in a small scale reproduction of the competitive idea. I mean, the NV-free by itself is definitely a competitive notion. So, okay, all right. So here is a simple approach that you can do, and which for several properties in these models works pretty well, which is to still use a reference to the context with divisible goods as a way to do an approximation. So in other words, we have this numerical value, the value of agent I, how much utility agent I gets from object A. Let's think of it. Let's think of object A as a divisible good, and of UIA as the marginal utility of agent I for any share of good A. So we embed the problem, if you want, in a standard Gale-Heisenberg, or even, it's a Gale-Heisenberg even with linear utilities, where we are dividing one unit of each good, which is divisible, and agents have linear utilities over the good. So if that's the case, let's look at the competitive equilibrium with equal income, right? Which will maximize the Nash welfare. And we will obtain a fractional allocation, an allocation in which certain goods will be divided between several agents. In fact, because of the linearity, it is often the case that you end up with situations where a lot of the goods are not consumed by too many agents. I mean, that's a fact that you can deduce in general. So there is a good chance that you can round up, approximate, that just saying, oh, this object was divided between two agents. Now I'm going to give it to that agent. And if you are careful, it could work. Unfortunately, turns out you can't. Turns out you can't. You have some. Here is an example. I don't want to go really through the example, but just to give you an idea, this is the counterexample that we have in the paper that's coming with one good object that is liked by everybody, agent 1, 2, and 3, because object A is worth 20, 15, and 10, respectively, for the three agents. And then 10 small object B that only agent 1 uses, 10 small object C that only agent 1 and 2 like, and 10 small object D that all the agents like, but they don't bring much utility. So you compute the CEEI, in which the only object that you can share is the first one. And why is that? It's because since agent 1 is the only one to like B, of course, agent 1 by efficiency should get all of B. Given that 1 gets all of B, then for the similar reason, agent 2 should get all of C, all of D. And then you get your competitive equilibrium, the CEI. But then you realize that if you start approximating what do you have to round up, you just have to decide who is going to get object A, right? That's the only rounding up options you have, because all the other objects are already assigned. And for instance, if you give it to agent 1, then agent 2 will envy agent 1. And if you give it, you check that. So you see the spirit, it just tells you that this rounding approach does not work. Okay. In this economy, if the right thing you have to do is forget about taking partial share, taking fractional shares, virtual fractional shares of the agent, but simply maximize the Nash product over all the allocations of the indivisible goods as indivisible. Just one good goes to one agent, and that's all. And it turns out that, you don't have to, we don't do the computation, but in this particular case would work. And you see, it's a little bit different. It's different in interesting ways, because it's not efficient. It would not give you an efficient allocation if you were embedding it in this allocation with fractions. But since you are actually not able to do that, it is fully Pareto efficient in this discrete economy. And here is the theorem. A theorem is that a partition maximizing the Nash product of utilities will be efficient, because of course it maximizes a collective utility, and it will meet the property of envy-freeness up to one object. Okay. All right. It is a difficult problem to solve. The maximization of the Nash product over all partitions, and there are some other ways to arrive at essentially the same solution with slightly different interpretations. The proof, I mean, very briefly, I want to, the proof is neat in the sense that it's just a simple argument, a simple counting argument, but one which is, which has to be done carefully. So it's by contradiction. You take a partition maximizing the Nash product, and you assume that still it's not envy-free up to one object, right? So there is one agent, there is at least one agent who envies another agent too, even after adding any object to the share of one, right? Or taking away any object from the share of two. So you take, since you have this situation between 1 and 2, you choose optimally the one object that agent 1 should be trying to eliminate from the share of 2 is the one in which the ratio U2A over U1A is minimum, right? Because this is the one where, from the point of view of one, it's the most valuable, as opposed to, with respect to how much agent 2 likes it. So, and then you say, okay, well, because this thing is not envy-free up to 1, it must be the case that after adding this utility of A star to the share S1, it is still below the utility of agent 1 for S2. So there is still envy. You see, instead of taking it away from S2, I added it to S1, which is the same. Right? So I have that, and then on the other hand, I have this other inequality that because A star minimizes the ratio U2 A star over U1 A star, it also is, this ratio is less than the U2 of the entire share S2 to U1 of the entire share S2, because this ratio is minimal for this particular component. And then you play with the inequality, you do the product, and you find that that by transferring simply A star from S2 to S1, you find by simply developing the inequalities that the Nash max product has increased. Okay? So you see, I mean, of course, it's difficult. It's too quick to do it in your head, but it's no more than that. It's a little bit of algebra, but cute. I mean, and it's a nice result because it tells you, well, EF1, you divide good. That's a program that you can achieve without any particular limitation. Okay. So the next step here has been to say, okay, this is good, but of course when you look at the proportional up to one object or NV3 up to one object, you realize that the object that you move around to achieve the property can be a very large object, can be very valuable. So sometimes it's really not telling you much. If there are objects that are very big, and that's one of them that you take away. Okay, so a natural strengthening is to say now, if you take at the proportional, for the proportional idea, now we're going to ask that in order to eliminate the NV, or in order to satisfy the proportionality ratio, the object that you have to add be any object, at least any object of some value to you in the share among those that you don't get. And so proportional X says that if your share is not worth at least 1/10 of the value of all the objects, but if now we add to your share any one of the objects that you don't get, provided that object is not zero. I mean, you can eliminate those kind of objects, it's not important. Then you achieve your level, okay? All right. And similarly for NV3 up to one object, if I NVs J, we can take any non-trivial object from the share of agent J, eliminate, and that will be enough to cancel the NV of I vis-a-vis J. All right, so it's clearly a much stronger demand. And when you start exploring this concept and you start with the proportional, which is the simpler one, you will see that we encounter immediate difficulties. But first a nice result, which is not trivial without being very complicated, which is that the case of two agents works well. The case of two agents works well because these two concepts, EFX and proportional X, can be satisfied. First of all, you check by similar kind of argument that I was doing before, that EFX implies proportional X. So you only need to look at EFX. Then you check that the Lexi-mean solution applied to normalized utilities. So here, in fact, for this particular solution, you introduce a bit of cardinality. But it's not really serious cardinality because it's Lexi-mean, so fundamentally it's ordinal, but okay. The Lexi-mean solution applies to a normalized utility, meaning that your utility for all the object is 1 by rescaling. Then you Lexi-mean, so you maximize the utility of those, the one who gets the smallest one, and among those you maximize the conditional. Upon doing that, you maximize the utility of the next lowest agent, and so forth. So that will be, of course, efficient because the lexicographic, the Lexi-mean ordering selects an efficient outcome, and it will be EFX. The proof, again, not very difficult, but still it will take you a few minutes to think it through. Okay, good. So maybe things should work for more than 2, right? Bad news. Even Pro-X does not work. Even Pro-X does not work. And here is a counterexample. I mean, there are others, but this one is especially simple. So you have 3 agents. Now we go immediately from 2 to 3, and we also have the same identical utilities. So that's also a case which should be easier. But here, so you see, you have 4 good objects, each worth 3, and 1 weak, inferior object E, right? And so it turns out, so here, what is your average value for all the goods? It's 1/3 of the total, which is 12 plus 1, 13. So it's 4 and 1/3. That's the level that you look at. And now you look at any allocation that has any chance to be fair. Of course, what will happen is that there will be an agent who will get 2 good objects. Because there are 4 objects, we have to distribute them all. So someone will get 2 good objects. That's going to be an agent who gets, for instance, BC. And then there will be the other 2 will get 1 good object each, and someone will get the bad object. So there will be an agent with AE, another BC, and the last one D. And of course, the choice of A, you can permute A, B, C, D, nothing changes. So now you look at the agent who is badly treated, who gets only D. So his utility is currently 3. He's looking at 4 and 1/3. But by adding to the share of D the small object E, that simply gets him to the level 4. And according to Pro-X, it should be the case that by adding any object that this agent does not get, he reaches the level proportional, the proportional level. So it's not Pro-X, but it is in fact EFX. It is in fact EFX because, well, look at D. He's certainly envious of both the agent who get AE and the agents who get BC, but his envy disappears if he eliminates the E from the first agent's bundle, and if he eliminates any of B or C from the second agent bundle. So you see that in this context, I mean, this example shows that here EFX works, Pro-X does not. So in particular, you don't have anymore that EFX implies proportional up to one object, up to any object, okay? All right. So situation becomes a bit more complicated. And then people have been asking, okay, well, Pro-X is not good, but EFX maybe also is impossible. I mean, after all, you know, we got this bad result with max mean going from 2 to 3 agents. This theorem, which shows that EFX is feasible in all 3 agents problem, is in fact the state of the art on the discussion of EFX. And EFX was proposed in 2014 as a good reinforcement, a good strengthening of the NV3 up to one object. And the question is whether it always exists or not is still unresolved, despite in a really large amount of research, right? And in fact, this result showing that for 3 agents problem, you can do it, has been in the making for a long time, and is quite a complicated proof. And notice that it also does not guarantees that it can be also efficient, right? It's not obvious, because when you start from an AFX who is not efficient and you improve it in the Pareto sense, of course you can reach the Pareto frontier, but you don't necessarily preserve the NV freeness. So this is a big open problem, which right now is considered the most important one to solve. We don't know. In fact, nobody really makes prediction as to whether there is a counterexample for later or not. It's just there. Okay. All right. Allocation of bads. Allocation of bads. Here I want to stress the fact that just like we observed for the classic, the Gale-Heisenberg economies, going from goods to bad produces some surprises and things which are a bit difficult to explain. Well, here too, this will happen, even though in a different way. I mean, so now we are dividing bad. And when I speak about this UI, I'm talking here of this utility. So for each object A, each agent has a positive number, a positive evaluation, but that's her disutility that we are trying to minimize. I mean, we don't use negative number, that's just a convention, of course, but I think it's a more natural convention in this context. Okay. So now just like you have for the case of goods, you can start by this idea of divide and choose, and what is the analog of the max-min share, this level of utility that you get by having the choice of choosing the partition. You choose the partition, but then you will be the last chooser. So now it becomes the min-max, by just because we are talking of these utilities, right? So the results are similar, and the numbers are different. and again, you know, there was a similar amount of research, which is by now kind of calmed down. There are also some interesting results which I did not put in the slides, but that I can report briefly. You could, in fact, dismiss this whole approach of the min-max and max-min in the sense that one property on which this impossibility result hinge is the fact that the ratio of the value of your utility for the different goods cannot be really bounded. There is a version of the model of division of allocation of these indivisible goods in which you postulate that for each participant, if you look at all the utilities, the utility from the worst object to the best, the ratio between the two is not too high. Or equivalently, if you normalize the utility of all the goods to one, the sum of the utility over all the objects, then the maximal value of any single object is bounded away from one by a fixed amount. And if that's the case, you can actually compute explicitly what are, if you limit the discussion to this particular domain, which is in fact fairly realistic. I mean, you could argue that, you know, most useful applications would have this feature. Then you can actually compute these functions max-min for the goods and min-max for the bad. And they are, if you are interested, I'll give you the reference, but they are horrible. They are functions which are not monotone in the utility UI. And with expressions which are not, which are rational coefficients, but very ugly, but still computable. So on the one hand, you could say, oh, maybe that's a good notion, but on the other hand, if you propose such an object to normal people, they would actually laugh because, so in fact, there is something fundamentally strange with this max-min, min-max in the context of indivisible goods. So that's that for that. Let's go to proportional and NV-free. All right. Now here, we do the same, we ask the same questions. What's interesting is that the techniques and the proofs are actually not the same. Okay, proportional up to one object. That means the proportional property is the fact that the disutility you experience for your own object is at most the average of your utility over all the objects. Okay, not the average. Sorry, the 1/nth share of your disutility for all the objects. So that is, of course, not feasible, but it will become feasible, it will be satisfied if you take away now an object from my share, which is a bad object. So now you make my share UI SI minus A, you make it lower in terms of this disutility. So that's now you're happy when you compare to the your nth, your fair share of the total disutility. And it is, proportional up to one object is compatible with efficiency. To show it is not so simple, but works actually by the approximation method that I mentioned before, which was actually a failure when we tried to achieve together EF1 and efficiency for the case of goods. In other words, you assume that those bads are divisible. You look for the some CEI allocation. You don't have to take, you remember that there are many, but you start from some. Here it shouldn't, it doesn't have to be unique. And then you do a rounding up exercise. It works because there is this fundamental structural property of the efficiency in economies where the goods are divisible and utilities are linear, is that any efficient allocation in such economies can be described in terms of its welfare by an allocation in which the graph of consumption, that is the graph which connects an agent to an object if and only if this agent consumes some of this object, that graph is a tree. You can avoid systematically any cycles in the consumption. You could have a situation where one consumes good A and two also consume good A as well as B, and three consumes B and C and one consumes C and A. This sort of cycle are possible but can always be eliminated because of the linearity. Because they mean that a certain product of marginal utilities is constant. So because you can describe efficient allocations like that, that's why the rounding up procedure will actually work for this goal. Okay, no time, of course, to go into the details, but okay. So it's already encouraging. Okay. Now here is the next step, which this time becomes really difficult. EF1, okay. EF1, well, that's NV3 up to one object, where you are able to choose the object. So if agent I envies agent J, agent I can remove this NV by simply dropping one of her object, which is a painful object. So therefore, she chooses the most painful of her own object, drops it, and she does not envy J anymore. It is true here too, for exactly the same reason that EF1 implies proportional up to 1. It is also true that it is achieved easily by the NFL draft mechanism, which, as before, is inefficient. And now the question is whether EF1 is compatible with efficiency. There is this recent paper that proves it, and it's quite complicated. It's a complicated algorithm, so there is no simple description. Maybe it will come when people, go over the proof and, But right now, it's a fact. It can be done, but don't ask me for the details. I can only. And it's a very recent paper, so it's possible that there will be some, some polishing and so forth and simplification. So it is possible. And that's really the extent of what we know in terms of positive results, to the exception of Pro-X. Pro-X, you remember, Pro-X in the context of goods does not work. And with this very simple example with 3 agents and 5 objects. But here, Pro-X does work, it turns out. Pro-X does work. What is Pro-X? Is the fact that if my share of bad things, bad chores that I have to do gives me a utility more than my fair share of this utility, by taking away any of my chores, any of the bads I'm consuming, I am now satisfying this thing. Okay? And now, what happens, there is a simple algorithm, but an inefficient algorithm, I mean, not one that gives you efficiency, to achieve Pro-X. How does it work? It's fairly simple. I mean, you have these utilities. I can describe it, in a minute. I mean, to give you the intuition. So you, for each of the bads, everybody has a certain level of this utility. So the natural thing to do to be sort of efficient, I mean, aiming in the right direction, is to say, if I start with a certain object, I should assign it to the agent for whom this utility is lowest. You have, of course, normalized your utility so that it becomes meaningful to compare okay. So you do, I mean, you order your objects without any particular care, and you start assigning to one agent with the minimal disutility for the first object. You assign to this agent that object. And you continue to the second good, the second bad, sorry, that you assign to the agent who likes it, who has the smallest relative disutility for it. You keep doing that until a certain agent, by the successive bads that he has to consume, now if you were to give him the next bad, he will pass over the critical threshold of 1/n of the total disutility. So in other words, if you were giving him the extra object, he would be beyond the proportional share, but by just one object. And now you realize that if you choose properly the ordering of your objects, making sure that this lowest disutility for each object go increasingly. So in other words, now you realize that the first object you could take is you should take is the one for which the lowest disutility is also the lowest among all the objects, and then the next one is a little bit higher, and so forth. So you realize that this person who is passing the threshold has received before some disutilities which were lower, and therefore now the property of proportional up to any object applies, and you can give to this person the extra object that makes her go above the critical level of 1/n, and still satisfy for the proportional up to any object. And because you have been penalizing that person a little bit extra, the problem that you are left with is one in which the relative position of the agent has in fact improved a bit, because we gave. So you see that's kind of the intuition. It's not a complicated algorithm, but the fact is that to understand whether this is or not compatible with efficiency is an open problem. Is an open problem, just like we have an open problem with EFX. I mean, EFX is not more solved in the case of bads than in the case of goods, right? And for EFX, just like for the case of goods, we don't know simply the feasibility. Of course, we know even less about compatibility of EFX with efficiency. So I think, I mean, I believe, I mean, I'm sort of optimistic that we will soon have a resolution of these conjectures and these open problems on the EFX and ProX. It's an interesting research topic. Unfortunately, it's not one that I would recommend to someone coming from mathematical economics and the standard game theory, because all of these difficult proofs, I mean, they involve really subtle algorithmic tricks. And we as traditional mathematical economists, let's say, we are not particularly well positioned for them. So it's up to them to tell us, where that theory will go. I am personally very interested, but you can still think of it as something to observe from a distance and see what else our colleagues in computer science and operation research will contribute to the fair division theory. Because I think here, if they crack those problems in a convincing way, I mean, it will be a really, really important contribution to the fair division problem. Okay, that's all I wanted to go over. Thank you for your patience and being still there after 4 lessons. I enjoyed it too. Oops. Okay. All right. There's someone with a question. If there is questions, yes, of course. Of course, time. Sorry.
Thank you, Professor. I was thinking about the goods example that you give, and somewhat free disposal thing, because remember that example. You have free, 4 frees, and only one. If we discard some good and made a fair share for maybe we think free and plus 1 to one of them and free to all the others, and the share is more equal. Not even free, not efficient, but
yeah. In fact, this is one of the things that is discussed in the literature, which is how many objects, if you are dividing k objects and you have n people, is there such a number p of objects such that if you could throw them away, all these concepts, indeed, and they do have some solutions, like for instance, n-1, if n is the number of objects, typically works. The problem is that those solutions are, well, they are very interesting intellectually. So far, it's not clear if they are tight enough to give some nice applications. But people are exploring all kinds of variants like that. Also, for the no-envy, you create a pool of objects with those that you discard, that you are not going to distribute, but you make sure also that nobody looking at her share would envy the pool of objects that are discarded and, if you want, given to charity or something. So yes, people think about those things, and it's there are many options, but the but the most, of course, the most appealing is the simple one, clear and easy. But you're right. I mean, that's one way. Yeah.
Thank you.
Thank you. Okay.
A quick announcement that lunch today will be on the fourth floor of this building and will be free for everyone. Thank you.
should wait 4 minutes.
Sure, sure. No, I just wanted to check if it works.
I wanted to ask you, do you know Ali Matziaki? Do you know Ali Matziaki? Ali Matziaki. He's also supposed to be in Tehran, some university, but probably not yours. Because he's a former PhD student of mine.
He was at OST?
No, he was in Frankfurt.
Okay.
But you don't know him.
No, I know two people.
Probably
with
you
the
are a mathematician,
same-
right?
No, I'm econ.
You are econ.
I know two people actually with that last name. I
With that
just
last
want,
name,
yeah,
okay.
that's why I'm asking where he got his PhD. I think he's at Tehran University.
Yes, maybe.
Yes.
Yeah.
Yeah. He's at
Yeah.
Tehran University. Yeah.
Well, actually, he invited me to come to Iran before war and everything, but I couldn't go. And you know what the reason is? If I go to Iran, I cannot go
cannot
anymore
to
to
US.
US.
You can actually go, but you need to get a visa.
But I won't get it.
No,
Probably.
you will, but
You will.
it has like, okay, we had this
Discussion.
problem. No,
Okay.
we had many people coming to our institute,
Yeah.
which is a new institute,
I see.
and we are private, so all those are public. We actually invited many people, and we had a couple of them coming. The problem is the American ones are fine.
Okay.
The one that are from EU, when they want to go to US, they have to go to US embassy, and it's like a half a day hassle that you have to have
Get over.
some yes,
Okay. Okay.
and then you will get, I think, 10-year visa. So for 10 years it will be fine.
Okay. I see.
But yeah, you will have 1 day at the embassy.
So the information for some people told me that I
No,
won't
that's-
be able to travel to the US anymore.
You will be, but you have to spend
I
1
see.
day at the
Okay.
getting
And
an
ask
embassy.
questions, answer questions,
Yeah,
and stuff like that.
something like that.
Yeah.
It's a half a day hassle.
Yeah.
That it's unfortunate. It wasn't like this before.
Before. Yeah.
This is something I think 7 years ago they started it during Trump first term. So
Yes.
yeah, it's made our life and
Be more
the
difficult,
people
of course,
yeah, we wanted to invite
Yeah.
more difficult. But if you anytime want to visit Iran,
Okay.
just email me or anyone at our institute. We're
Well, I
happy to.
would love to do it at some
We would
point.
be,
Yeah.
yeah, we would be happy to
Get
arrange
visitors, yeah.
everything for
yeah,
you.
yeah,
We can
yeah.
do everything much better than
Yeah.
public universities.
Oh, really?
Yeah,
Okay.
yeah. We have a good team, and we
Yeah.
have the experience, and we have the financial support, and we have,
Okay.
yeah, we can do, and we can arrange for other cities if you want
Okay.
to visit.
Okay.
We can do a lot of things.
Yeah. If you ever meet Ali Matziaki, say
Yeah.
greetings to him.
Sure, I just wanted to check your name to tell them that I saw.
Yes.
Yeah.
So you want to take a photo?
No, I remember.
Yes, but yes.
Yeah.
If you want to visit my talk, I will have the talk later on at 3:20.
Right.
Will be about repeated games.
That's too
Replacing
difficult.
players by algorithms.
Oh, interesting.
Yeah.
It's kind of difficult repeated game for me, but yeah, I would
Okay,
love
don't
to.
worry.
Thank you
Yeah.
very much.
We make stop.
I'm happy to wait 1 or 2 more minutes, but depends on. I can finish 1 or 2 minutes earlier. Yeah.
Would you please use the mic? No, no, it's not yet.
Not started yet, yeah.
No, I'm saying
Definitely.
he asked me to introduce you.
Oh, thank you very much.
So as Pradeep didn't want to introduce him, Behrang, right? I'm going to do it. We just had a little conversation about traveling to Iran, and I told him the story that I had a PhD student who now is a professor in Tehran, and asked him if he knows him, and he said, no, I don't know him. But actually the story is, it's Ali Matziaki, and he, at one time, he invited me to come to Tehran. And then I had to decline that because other people told me, if you go there, you cannot go anymore in the US. And now he just told me that's not the case. I would have to go to the American embassy and have an unpleasant half a day or something, answering questions, things like that. So maybe this is interesting for you as well. So thank you for coming, and the floor is yours.
Thank you very much, and thanks everyone for being here on Sunday afternoon on the last day. So I'm at Tehran Institute for Advanced Studies. This is a new institute, less than 10 years old in Iran, and we are happy to invite all of you if you don't have problem with US Embassy after that. Anyway, if you want, just drop me an email. I would be happy to arrange everything. I'm going to present my paper. There is no online version of it yet due to this situation, but if you just email me, I can send you a draft, or in a month or two, I will put a better version online. This is with my student. He's an MSc student, so he will apply for a PhD program. If you want good students, look for our student. What we are going to do is we are going to look at matching markets, and we are going to ask a different question than what you all see in this workshop. The question that we are going to ask is, what happens if the clearinghouse, the third party of the two-sided matching, is not fully committed to run everything that we ask for? So there are two things, actually, that the clearinghouse can do. It can change the algorithm and run something else instead of the one that he announced, or it can change the input. And what we are going to do is we are going to commit the clearinghouse to the algorithm. So it's going to run exactly the same algorithm that it's supposed to do, but it's going to change the input. And we are going to ask if that change can do something. Is there any effect to that change? The answer is, well, yes. It depends on the algorithm, and the change is going to be minimal for the most used algorithm we all like. So if you want to run differ acceptance, for example, a student proposing differ acceptance, you imagine that a clearinghouse fully committed to the algorithm will give you student optimal matching. We show that if we just add one dummy student, I will talk about what dummy student is, and if that one dummy student is designed in a right way, the clearinghouse can implement any stable matching that it wants. Specifically, it can do the school optimal stable matching. And if you check the algorithm at the end, you read the code, everything is fine. Let me talk about real life for a minute. So these dummy students are our abstract way of modeling things, but they actually happen. Not in the way that we use them, but they happen in some other way. For example, this is a story of last year. These organized crime rings, it was very interesting for me. They use AI. They enrolled more than 200 fake students. They had 1 million fake applicant, and they got $11 million in the federal aid by running these fake students. These students were actually submitting homeworks.
Where was that?
In the US, college, different colleges in the US, especially California. In the US, yeah, federal money of the US. They get some financial. Yes, but they get some financial aid and loans and so on. And if you have fake IDs and you put a fake assignment by AI, you get some money. And in response to this, the federal government actually last year, first in the June, they announced some identity validation, and for fall semester, they put a lot of screening process. But the point of this story is, this is absolutely different than what we do. The point is, if you can have 200,000 fake student, how much you're going to restrict it to get it to 0. We only need 1 dummy student. And just 2 more real life examples, then I will get back to the math. There was this scandal, it's very famous, very publicized. They run it from 2011 to 2018. There were many court cases, I think 30 something parents and so on. What they did, they paid money to get athletic something under their kids' application. They bribed some officials. There were 2 firms involved. There was very elaborate kind of scandal. And there are some famous people there. So if you check the Wikipedia page on that, it's interesting. And one last thing about manipulating the input. It's the Boston exam. This was actually an error, so it wasn't deliberate kind of scandal, but they made an error in converting some grading system to something, and then there are many applicants displaced. Let's get back to matching. So the usual question about incentive game theory in matching is about the 2 sides of the market. Are students going to say their preference truthfully? Are the school going to announce their capacity truthfully, and so on? And the question we are going to ask is, how about the third party, the one that's running this algorithm? And this, I will talk about the literature, but the one thing that we are going to look at is the changing of the input. This is kind of new in this question, at least. And something that we're going to do is basically, we're going to keep, okay, this doesn't work. We are going to keep the preference of a student fixed. That's not going to change. We are going to keep the capacity of schools fixed. That's not going to change. We are going to add 1 dummy student. This is going to be put in some place in a school's priority without changing other students' priority. So the real students' priority relative to each other is fixed. The only thing we are going to add is 1 ghost student, that we call dummy student. This is going to be placed in the priority of each school in the right way. And at the end, this is, I think, very important. This student is going to be unmatched due to the algorithm. So if you go and ask people, did you submit your true preferences? Did you, okay, not true preference. Did you submit your preferences? I wanted to check with what the algorithm did. You will get the answer, yes, everything submitted the preferences and the algorithm exactly did that, except this 1 student which is unmatched, nowhere to be found. It doesn't exist. So remaining unmatched, I think, is very important. Now let's talk a little bit about the literature. So the start of, I think this literature is Akbarpur and Lee 2020 paper. It's called Credible Auction. It looks at the auctioneer and says, okay, there is this third party in the auction as well. You have buyers, sellers, this third party can change something, and ask if different auctions are credible or not, and then show that there is this trilemma where the first price action is good in some sense. So there is a huge literature coming out of that. I think there was a talk in this workshop about the credible auction as well. Now, this literature extends to matching. As you can imagine, the matching literature started doing it on the mechanism as well. So they started looking at the algorithm and see which algorithms are credible in some sense, and you can manipulate and get something else, and so on. So there are these at least 3 papers. The last one is T 2026. They show that, okay, DA is not good, what we get as well. They compare it with different mechanism, and then this one I like the most. This says how many people's preference do you need to check whether the algorithm was run properly.
You're saying that introducing one dummy student by the university, say, okay, by the government, will improve the assignment for that university?
So I should be clear. There is schools on one side. There is a central clearinghouse. You want to call it government. Yes, that government can introduce one dummy student and change the assignment of everyone to any stable matching that it wants. One, you can change everything. So there's a couple of million students some place and schools. One dummy student is enough to change everything. Yes. Any stable matching on the lattice you want, you can pick.
Instead of getting the best for the student, you get something better for the
Better for university, something fair, anything that you want, we can do it. And it's actually very interesting. We construct it. It's very easy. It's not existent. We construct that dummy and we show how it works. How we do it, we basically borrow from these 2 papers. So the main paper that we use the technique is Kesten. It uses the rejection chain technology that we're going to use for something on the opposite side. It asks the students, are you going to give me your consent if you're part of a rejection chain to change the assignment of everyone else, but your assignment is the same? Are you going to give me some consent that I drop you from this rejection chain and improve other students? So in that paper, the designer is going to Pareto improve the assignment by changing the existing students' preferences. And then there is this paper, Afakon 2014. It's basically what you asked me. It looks at one school. That the school is going to design something called fictitious student. And that student is going to be either unmatched or matched to the same school. And it improves that school only. It doesn't respect stability and so on. It improves just one school's assignment. So let's jump into the model. It's exactly what you would imagine, many-to-one model, 2-sided NTU, set of schools, set of students, preference of schools. You have quotas for each school, so this is many-to-one matching. But for examples and the proofs, I will just show one-to-one matching. And then you have priority for schools. It's going to be responsive, and you put these together, you have the problem. It's exactly what a standard many-to-one matching of school choice you could imagine. And again, exactly the standard definitions. You have a matching mu from students to school that respects the quotas. You have a mechanism that gets a problem, give you a matching. You define a stable matching the same as usual, and you have the lattice structure that we're going to work with. So this is the lattice of a stable matching that we're going to use. And this is the new part. So you have a problem, you define a new problem. How do we define it? There is a new student D. The set of a student is going to have this new student. The set of a school is the same. The set of preference for a student is the same, plus this new element in the vector for this dummy student. The set of quotas or capacity is the same. And something changes a lot. That's the priority of the schools. Yes.
You're going to use the student proposing procedure.
Yes. But you can do anything you want. Preference of dummy, I will talk about. It doesn't matter that much. It's just there, PD. This is the preference of dummy. Oh, this is the new market that we are, this new problem that we are designing. So the only difference from the previous one, everything extends in the same way that you think, except the priority of a school is going to change more than you expect. And the way that we define a dummy student, we fix a problem, we fix a mechanism. Yes?
How do the schools place the dummy in their list?
I will.
Can you control that? Or
Yes, yes.
you're going to control that?
Yes, that's the whole point. I will explain that completely. In few slides, that would be the construction. So if we fix a mechanism, then we can define a dummy. So the dummy depends on the mechanism and the problem that you're looking at. You fix a mechanism, you fix a problem, then we call this student D, a dummy student, if it's going to remain unmatched at the end of this mechanism on the new market. The preference of previous students is exactly the same. Their relative priorities in the school is exactly the same. The relative preference of real student is the same, but the new one is inserted in some specific place.
I can understand the dummy school ranking the colleges of the schools any way you want.
Yes.
It's harder to understand how you force the schools to put the dummy where you want. How
So,
do you force the schools to place the dummy in their ranking where you would like them to? You
So-
being the manipulator.
I agree with you. That's a little bit challenging, but let's look at you as a school choice. How you put priorities of a school. It's fixed. It's based on some rules. If you know the rules and you know the priority, you can say, okay, this student is in this neighborhood with these exam scores, so it should be here. Let me show you one example, and I think it will be clear. I'm not doing something difficult. It's very easy, just some small trick there. So we have 3 students, 3 schools, and preference and priority are cyclical, so we get 3 stable matching. So student 1 prefers A to B to C, and then 2 prefers B to C to A, and so on. You have 3 stable matching. The first one, each student wants is a student optimal stable matching. The first one that a school wants is the school optimal stable matching, and the one in the middle, which somehow you can consider it a fair matching. Now, if we do the differ acceptance, as there is no rejections, every student would propose to one school. Each school has 1 capacity and 1 proposal. We are done. So this is the student optimal. Now let's construct this dummy student. How do we do that? We pick a target. We want to implement one of the other 2 stable matching. For example, here we want to implement the school optimal. How do we do that? We put the dummy student exactly after the assignee
in the targeted matching in the priority of the schools. So the dummy student is after the target matching in the priority. You do the differ acceptance, you start the rejection chain. The rejection chain is going to displace students and so on. And I will explain exactly in the proof of theorem, if I have time, what's going to happen. But the idea is at the end, this dummy student is going to be rejected from everything. And the one that you targeted is going to be the result of a student proposing. So let's talk about the theorem.
What assignment do we get here?
You get this, which is the school optimal. You run the student optimal, you get the school optimal in the original problem.
But this condition that he remains unmatched is a condition of the manipulation you are able to do. I mean, not any manipulation you can do.
No. This is the manipulation that I define.
I know, yeah.
And I'm showing that I can do everything with it.
Okay.
If I can define something that is very strict, but I can do everything that I want with it, that should be good. So a theorem and the proposition. So the theorem basically says, pick any many-to-one standard matching that you want. Pick any stable matching that you want for this problem. So that's the mu. I'm claiming there exists a dummy student, that I add this dummy student to the original problem. I run a student proposing differ acceptance. I get the stable matching that you wanted. I will show you a sketch of proof in a minute. Just let me give you this as well. It's interesting. So can we do something else with the dummy student? The answer is no. All attainable sets that you can get from any dummy student that you pick at random is exactly the set of stable matching of the original problem. You cannot get some unstable matching with some random dummy. Any dummy you pick at random, you will get some stable matching. These two sets are exactly equal. So let me ignore this and tell you the proof. The proof is for one-to-one here. It extends to many-to-one easily. So you fix a stable matching. You extend this stable matching mu to mu tilde by adding the dummy student. The dummy student is unmatched, so you know what dummy mu tilde is. And this mu tilde is stable in the new market, right? Everyone is there. There is individual rationality. There is no blocking pair because you started from mu, which was stable. So the mu tilde is stable in the new market. Now this is the key point. You have rural hospital theorem. Rural hospital theorem tells you that this dummy student is going to be unmatched in every stable matching of the new market. And because it's going to be unmatched, if you pick something else from a student proposing differ acceptance, you can form a blocking pair. How do you form a blocking pair? Assume you find mu hat from running a student proposing differ acceptance. In the mu hat, the students are better, so schools are worse. That's the lattice structure of new market. So there is at least one school that's worse in mu hat, and we put the dummy student where? Exactly below mu tilde. So that the dummy student is above mu hat. They're going to block, and that's the idea. Any question this so far? Okay, what else? This is actually a huge problem. Why? Because if you have any kind of heterogeneity in school priorities, there is always an instance of student preferences that I can manipulate. So it's not a one example impossibility kind of theorem. You have any problem that is not serial dictatorship, they don't have exactly the same priority, I can guarantee you there exists a preference for a student that my manipulation work. Yeah.
The only one stable matching?
Oh,
But
yes,
references
yes.
are not the same?
Yes, if you have one stable matching, I cannot manipulate. That's why I'm saying you pick any school priority. There is an instance of student preferences that you have multiple matching and I can manipulate. Not for every preference and every priority. You give me a preference of schools, there is a preference of a student that this kind of manipulation works.
So I just clarifying, I think you said it already. So you can create a dummy student easily and with the ranking on the schools, that's easy to understand. And because he's not unmatched, he won't be detected. The problem is how do you insert him where you like in the college's preferences? And you are saying we can create fake certificates, we can create fake identity, so that the school will place, if you knew how the school is ranking, you could place him where you want. And that's how the AI can manipulate the system.
Yes, the clearinghouse can use
The clearinghouse,
yes,
all right,
yes.
the clearinghouse.
Because at least in the US, I know that the priority of schools is based on a rule.
Okay.
So they cannot say I have.
So the clearinghouse has to understand how the schools form preferences so that it can put the dummy wherever it wants in their preference.
Yes.
You are using that fact in your proof.
Yes, yes, yes,
Okay.
yes. That's true.
All right. Thank you.
Thank you.
Position 2 is not great news. I mean, because this is very limiting. This condition is very strong.
Yes,
That they share the same order. I mean, which means that mostly it is manipulable.
Exactly. That's if and only if, and the only if part is interesting. I agree with you. The if part is nothing, but the only if part is very interesting, I think. This is a huge problem. One more thing. There are two other mechanisms, Boston mechanism and top trading cycle. You cannot do this there. Why? The answer is because the dummy has to remain unmatched. In Boston mechanism, if the dummy is going to displace someone, it's immediate match, it's matched, you have a contradiction. In top trading cycle, the same. If it's going to displace someone in a cycle, it's going to be matched in that cycle. So it's not going to be unmatched, we are done. Now, 5 minutes, two more applications. First one, let's look at matching with constraint. This is based on Kamada and Kojima and many other works by Kojima and his co-author. You have the same problem. Instead of a stable, you call justify MV, and it's exactly what you can imagine. If there is no justify MV, we say the matching is fair. You define something called general upper bound. General upper bound means if a set of students are feasible at a school, any subset of that set is feasible as well. So it can incorporate most of the things that you want: diversity, budget constraint, anti-bullying, daycare ratio, and so on. There are only a couple of things that you cannot. For example, the floor constraint or minimum constraint, as it's called, general upper bound constraint. And based on Kojima's work, we know there are fair matchings. They form a lattice, same as stable matching. Here I need one more kind of dummy student. This is actually called fake student. And basically, these are very easy. They are going to be designed for one school. Their preference is just one school. They're going to get matched to that school, and they're going to be on top of the priority of that school. What they do is they reduce the capacity of that school. That's it. So these are what I need, but I need several of them. It's not just one, but what they do is basically they reduce the capacity. So if you can reduce the capacity, you just need a dummy student. I only need one dummy student, I get this result. I think this is interesting as well. So you have a matching with constraint. You don't want to announce the constraints. Your centralized clearinghouse, you want to get some matching that respect your constraints, and you want to implement one fair, feasible, individual irrational matching. They have a lattice structure as well in this setting. You pick one of them, you add one dummy and several fake students. You announce, I'm going to run a student proposing differ acceptance without any constraint. You run that, you get the matching that respects your constraint. Okay, let me show you a little bit how it's done. I got 2 minutes, okay. So what I do is basically I pick a fair, feasible, individual irrational matching. Yes.
Fake can be matched with the
Yes, fake students are matched. They are not that difficult to construct. They are on top of the school that they're designed for, on top of the priority, and they accept
they
only
just
that
have
school.
less students,
Yes,
effectively.
they're just filling out the capacity of one school.
Thank you.
They don't do anything. I can just say I reduce the capacity. So basically, first I reduce the capacity, I fix a fair, feasible, individual, rational target matching. I look at the quotas, I look at the number of students that are matched. The difference are the number of fake students I needed for that school. So I put the fake students here. I reduce the capacity from 4 to 2. After I do that, I'm going to show you this is not going to block. Let's ignore this. I have 2 minutes. Let's do this. I pick that. I add fake students. And then I apply theorem 1. And it's easy to show that it's going to be the same matching. It's going to respect all the constraints that you had at the beginning. It's going to be fair. Last thing. So can we do it for matching with contracts? The answer is yes. You need these 2 standard assumptions. If you add these 2 assumptions, you get the same result. Here you don't need fake students. You just need one doctor and several contracts for that doctor. If you add one dummy doctor, you add a couple of contracts for that. You pick any set of a stable contract to begin with, you run Doctor Optimal, and you get the one you wanted. This is, I think, one of the practical application in NRMP. And thank you very much.
Thanks very much. Thank you. Okay. Ah, what? All right, thank you very much. Thanks for being here right at the end. This is joint work with Kishore Gawande. I'm Ben Zissimos, and the title is How and Why Dictators Use International Trade Policy to Forestall Democratization. This is an exercise in applied game theory. Despite 3 waves of democratization, much of the world remains under dictatorship. According to Freedom House, who take great care in measuring these things, 49 countries are in dictatorship now, representing nearly 2.7 billion people, or 37% of the global population. Moreover, and perhaps this is the more worrying fact, there has been no forward movement in democracy for the last decade. In fact, by some measures, democracy is in decline. Yes.
China is included in 49 countries.
Yes, correct. Yes, China is a dictatorship indeed. So while the existing literature focuses on understanding the process of democratization, the challenge now is to understand how it is that some countries remain entrenched in dictatorship. And that's the challenge that we're taking up in this paper. So the literature, and by the way, I'm happy to take questions as we go along. The literature on dictatorship and democratization concentrates on who has the power to tax whom and why. So Acemoglu and Robinson, in work that started in a now famous QJE paper in 2000, Why the West Extended the Franchise, and in giving birth to a huge literature and earning them a Nobel Prize, argue that the purpose of democratization is to allow a ruling elite to make a credible commitment to the rest of society using domestic taxation on a sufficient scale to diffuse the threat of revolution. So Acemoglu and Robinson's idea is that the ruling elite face the threat of a revolution, and they have to be able to make transfers to the rest of society on a sufficient scale as to give them what they could have gained from revolution in order to stop the revolution from happening. But they can't lay their hands on that much resources in a single period, and so they have to be able to make ongoing transfers over time. And it's democracy, it's handing over the power to tax through democratization that is the mechanism that lets them make the commitment to ongoing transfers. Okay, that's Acemoglu and Robinson's Nobel Prize-winning idea. But the empirical fact that has come to light since their work, uncovered by Aiton and Jensen and Dodlover and Lucas and others, is that dictators tend not to install domestic redistributive fiscal capacity. Dictatorships don't have income taxes. China doesn't have income taxes. What they do all have is trade taxes. Okay? All dictators have the capacity to tax goods at the border. And so, in a sense, that if we, that's the agenda that we're taking up here. Now, in a sense, if you're only worried about democratization, the policy instrument isn't kind of central to the narrative of what goes on. Indeed, the enormous empirical literature in this area on democratization simply says, do we observe the threat of revolution? Does that causally identify democratization? Yes, okay. We've shown that Acemoglu and Robinson's prediction holds in the data. However, if what you want to do is show that as a result of a threat of revolution, you don't get democratization, then it becomes more important to be able to tell a story about the trade policy, about the policy instrument that the elite use to prevent democracy from going ahead. And that's what's important here. Yes.
If I assume that the revolution could have achieved democracy,
yes,
then you're saying dictatorships can replicate democracy by international trade.
Yes.
They do the same thing that democracy would have done.
That's right. That's how to think about this. So
That's what you're saying.
That's what I'm saying. So, and a classic example of this, you know, the most studied episode of trade policy in history is Britain's repeal of the Corn Laws. And so this is where England in the 19th century, the ruling elite had installed the Corn Laws. They was basically tariffs that protected their income. And the people moving into the factories wanted cheap food. They wanted free trade. And the argument goes, they wanted democracy so that they could get control over trade policy and get free trade. And the repeal of the Corn Laws was basically the ruling elite saying, we know what you want. We know what you want is cheap food. We're going to give you the cheap food. We're going to repeal the Corn Laws. Don't worry about democracy. And the people took it. That's what we're modeling here. Okay? All right. So that in a nutshell is what we're saying here. Responding to this point, in a paper that I published in the Journal of International Economics in 2017, I combined the underlying political economy logic of Acemoglu and Robinson with Mayer's Heteroline model to develop a general theory of how dictators use trade policy to diffuse the threat of revolution. That paper shows that the elite may be forced to democratize in order to diffuse the threat of revolution, just as in Acemoglu and Robinson, but there is a range of the parameter space over which they may be able to use trade policy to forestall democratization, just as in the Corn Laws story. And I'm going to show you, I'm going to characterize equilibrium, and I'm going to show you the range of the parameter space over which these two outcomes happen. So in the prior literature, the threat of revolution arises exogenously. So it cannot be linked to observable phenomena. Our first objective is to develop a model in which the threat of revolution is endogenous, and it's endogenous to world price shocks. Okay? And so these are an observable phenomenon. And this opens the door to the empirical study. We don't do econometrics in this paper. It's laying the theoretical foundations that will open the door to being able to look for these patterns in the data. The second objective of this paper is to demonstrate formally why, and in particular under what conditions, dictatorships will use trade policy instead of domestic redistributive taxation, instead of income taxes, to diffuse the threat of revolution. So what we're going to do is introduce the option to install domestic redistributive fiscal capacity, and then show that installing this more efficient tax instrument can make it more difficult for the elite to forestall democratization. Okay? So that's something they're not going to want to do. They're not going to want to make it more likely that if the threat of if a high world price state arises, that they're going to have to give up power through democratization. So they're not going to install the domestic redistributive fiscal capacity, and that's going to give them an incentive to stick with the less efficient means of taxation, with trade taxation. So here's the model in a nutshell. Initially, a ruling elite control a government outright, where here the focus is on control over trade policy. The elite are landowners. We're thinking of a country at a relatively early stage of development, where the elite are landowners, while the rest of society rely on labor income. The production structure is heteroline, and the appealing feature of that is that there's a tension over trade policy. So the ruling elite own the abundant factor, they own land, and they want as much openness as possible. Through their factor abundance, they produce food relatively cheaply. They want to export as much as possible in order to chase higher world prices abroad. And it's the scarce factor, the labor that is used intensively in manufactures, that wants protection. If you're scarce, then you're relatively expensive. That means you produce manufactures relatively expensively, and there you have competition from foreign goods that will compete down your wages. Okay, so you actually want, the scarce factor wants protection. That's the key kind of general tension over policy between the rest of society and the elite that we incorporate through the Hector-Ohlin framework. We initially assume, yes, we initially assume limited domestic fiscal capacity. In fact, we start by assuming there is no fiscal capacity by assumption. So redistribution must take place via trade taxes, and we later endogenize the installation decision. Yes. Yes.
This country is producing only food and importing manufactures.
Thank you for clarifying that.
Is that what you meant?
That's not what thank you for, I'll clarify that. Thanks for raising that. So this country is producing both food and manufactures. They have a comparative advantage in the production of food in this example. And so they produce food relatively cheaply, and so they're going to import manufactures. The who owns so both so land, these are good, very good clarifying questions. So in the Hector-Ohlin model, both goods require both factors. However, food is intensive in the production of land, whilst manufactures are intensive in the production of labor. So it's the land-intensive good that you produce relatively cheaply if you have an abundance of land. Okay, it's food that you produce relatively cheaply if you have an abundance of land. It's manufactures that you produce relatively expensively if you have a scarcity of labor. However, both goods do use both factors. Yes. Okay. Let me also say that initially we're going to assume that the country is a dictatorship, and then we're going to explore whether the ruling elite can maintain dictatorship, okay, through manipulating trade policy, or whether they eventually have to give up power either voluntarily or through the threat of revolution. Okay. The rest of society are too poor to lobby financially. There's no common agency, no Grossman and Helpman, no menu auction in this framework. But they may be able to exert influence through the periodic opportunity to mount a revolution, triggered by random world food price shocks. Under the threat of revolution, the elite may face a commitment problem, as I said, just as in Acemoglu and Robinson, in which case they'll democratize to make a credible commitment to trade policy preferred by the rest of society, but they may be able to use trade policy to diffuse the threat of revolution and forestall democratization. Okay, let me skip the literature in the interest of time. So here's the model. There's a single small country that takes prices as given. Each citizen is placed in one of two groups, either the ruling elite, which we'll denote by epsilon, or the rest of society, which we'll denote by rho. And each member of each group is identical to every other member in that group, but differ vis-a-vis the other group. So we're going to be able to reduce this to a two-player game. Production structure is Hector-Ohlin, extended to an infinite time horizon in order to enable us to capture the commitment problem. And the elite are endowed with land, as I was saying, and the rest of society are endowed with labor. There are two goods. Good epsilon, think of food, is land intensive, whilst good rho is labor intensive. Think of this as manufactures. And really, you only need to remember that one piece of notation out of all of this, which is P, the relative price of food. Okay, manufactures the numeraire here. So we're looking for an increase. A periodic food price shock is an increase in the price of food. We're also want to think about world price and the autarky price, respectively. So we can define payoff functions for the respective groups J being either the elite epsilon or the rest of society rho, as the indirect utility function. Everything in this model can be defined in terms of prices. Consumption is obviously defined in terms of prices. Income is defined in terms of prices, so we can define everything in terms of prices. And these are concave functions, so we can differentiate to obtain what we call the preferred price levels of the respective groups. And what we have is that the ruling elite want a preferred price level is higher than the world price, while the rest of society's preferred price level is lower than the world price. Okay, if you produce food, you want as high a food price, you want a relatively high food price. If you consume food, if you're a net consumer of food, you want a relatively low price. Okay, and these are the ideal, these are important because they denote under elite rule, the elite are going to seek to set this price as much as possible, whilst under democracy, where the median voter is a member of the rest of society, they're going to seek to set this price as much as possible. Okay? Yes?
Will you take PW as exogenously
Yes.
given?
Yes, I will.
There's no world trade equilibrium here.
There is, but that's the significance of the small country assumption. So there's nothing that this country can do to affect world prices, and that's the sense in which we take it as given. Okay, I've described that. So let me characterize how world price shocks work. So the concept of equilibrium here is Markov perfection. So we're looking to characterize the stable equilibrium in which the outcome in each period is defined strictly in terms of the state. So the state variable here that changes is the world price. And that oscillates between low and high. Okay, and we'll sort of interchangeably say that the world price is low or high, and say that the sort of threat level is low and high. Low world price is low threat, high world price is high threat, thinking in terms of a world price shock. And this, of course, remember, is all world price of food. So with probability 1 minus kappa, the world price level is low. With probability kappa, the world price is high. And then what follows is, of course, that the elite like it when the world price is high. This raises the income that they make from land, whilst the rest of society dislike it. They want cheap food. So they're better off during normal times where the world price level is low. We capture revolution through a radial contraction of the PPF. Okay, this is making use of an idea due to Paul Collier called the disruption cost of revolution, or the disruption cost of conflict, whereby as the conflict prevents factors from matching with their kind of productive uses effectively. Okay, so this preserves all of the slopes in the model. Without this assumption, you'd have to deal with ideal price levels differing across revolution and no revolution states, would make things very complicated. So this radial contraction approach is a kind of very useful here in this context. Now let me give you the value functions under the three different outcomes that we're going to want to consider: democracy, revolution, and elite rule. The first one to consider here is democracy, where so VJ, this is the value function for a member either of the elite, epsilon or rho, rest of society, under democracy. That's what's denoted by D there. The first term gives us the welfare level of that member of that group under p hat rho in state S. Why p hat rho? Remember, this is democracy. This is where the median voter, a member of the rest of society, gets to implement their preferred price level. Why S? Well, the first term depends on whatever the state is. If it's the level of welfare under the high or low price outcome. And then the continuation payoffs are given by kappa times the probability in the future that we have a high threat state, and then 1 minus kappa times the probability that we have a low threat or low world price state. Okay? And then these continuation terms are discounted. Yes? Beta is the discount rate. It's just how much you discount each subsequent period. Yes?
Didn't understand so far who are the players. Are the members of the groups the players, or are the groups the players?
Good question. So we are assuming that each member of each group is identical. So we're reducing, so we can think of this as a two-player game. We're reducing it to a two-player game.
But deviations, that matters a lot. I mean, if a member is small relative to a group, then a member deviating actually doesn't change much. But if the group as a whole changes, it is a big difference.
So we're adopting the same approach as Acemoglu and Robinson have, that if any player deviates, then all players are going to have an incentive to deviate. Okay.
Somewhere are you using mathematically the fact that epsilon is much smaller than rho?
It's not, doesn't have to be much smaller than rho. The only critical thing here is that a member of the rest of society is the median voter under democracy. That's all we like. So it's a half. As long as epsilon is less than a half, that's it. That's all we need. The value function under revolution is the same as under democracy, except that in the period where revolution happens, radial contraction of the PPF, the level of welfare is lower in that period. Okay, then everything goes to the same as under democracy, and then finally the value function under living with the status quo of elite rule. Here you do since the elite are in power, it's the elite who set the trade policy. Okay, hence the epsilon here. Okay, so now crucially, and this is important, in the low threat state, the elite cannot credibly commit to do anything other than what they want. Okay, this is Acemoglu and Robinson's observation. When the threat level is low, the elite can't credibly commit to do anything other than what they want. It's only when the threat level is high and they face the threat of revolution that they can credibly commit to say, okay, now we can do what you want. Now we can do what the rest of society wants, in which case we can play around with doing something that gets you towards the level of welfare that you could have obtained under revolution. Okay? So it's those crucial periods that end up being important. Okay? Let me, let me go to the characterization of equilibrium, and if you want to see anything about the sequence of events, I'll come back in the interest of time. So here, this figure illustrates the characterization of equilibrium. So on the horizontal axis here, we have kappa, the probability that in any future period, the threat level will be high. And then on the vertical axis, we measure the complete, the fully discounted payoff of the rest of society. And what we're assuming here is that we're in a high threat, high world price state. Okay? And the top line there, downward sloping, is the payoff to democracy. All right, this is the best that the rest of society can do. They get to set the exact policy that they want in every single period. Why is it downward sloping? It's downward sloping because this represents a higher probability that in any future period, the price of the food is high, in which case their welfare is lower. The next line down tells us the payoff to revolution. Why is it lower than the payoff to democracy? Because revolution is costly. Okay? And then finally, this line here is the payoff to the rest of society of living with elite rule. It's the maximum level of welfare that the elite can induce for the rest of society, can credibly commit to induce for the rest of society. And the significance of this line is that it's dependent on the number of periods in the future where the threat level will be high, in which case the payoff to, in which case the elite can commit to setting the policy that the rest of society wants. Okay? In every other period where the threat level is low, they can't commit, they set p hat epsilon. And what we see from this diagram illustrates the commitment problem, or where the commitment problem applies. So over this range, we see that the most that the elite can induce for the rest of society is still below the payoff to revolution. This is the range over which, if the high threat occurs, the elite have to extend the franchise, okay, in order to diffuse the threat of revolution. It's over this range here that the best that the elite can do for the rest of society is actually above what they could get from revolution. Over that range, the elite can use trade policy to diffuse the threat of revolution. Okay? So it's over this range. So we get this sort of surprising result that it's actually in a more volatile environment where the high threat state arises more frequently that we get that they don't have to diffuse, they don't have to democratize in order to diffuse the threat of revolution. It's when world price shocks are more unusual that they actually end up having to do that. Here's the proof of, so what the approach we take is to first of all, by the way, this is by assumption, and again, this is an assumption inherited from Acemoglu and Robinson. In order to have any situation where where the elite face this commitment problem, you have to have that the intercept of the payoff under elite rule is below the payoff under revolution. Okay, and what we're able to show in endogenizing this threat is that providing the price level is sufficiently low, in the low threat state, the threat of revolution simply never arises. It's never worth it. Food prices are low enough that given the cost of revolution, it's just never worth it. And the threat of revolution never arises under the low threat state. When the world price goes high, then you get a situation where over a certain range of the parameter space, democratization does become worthwhile. And then finally, the question of why the elite would ever would use trade policy rather than more efficient instruments. Here we set it up as Acemoglu and Robinson. So we're saying, all right, start with trade policy. Now ask if the elite would like to install the capacity to do Acemoglu and Robinson, to impose lump sum taxes. What does that do? Well, we know if lump sum taxation raises the payoff that the rest of society, if the elite's installation of lump sum taxation raises the payoff that the rest of society can obtain under democracy, then relative to under elite rule, then what we see in the shift up of this black line to the red line is this critical point moves to the right. The commitment problem applies over a wider range of the parameter space, installing more efficient taxation, making it easier to make transfers, larger transfers between the elite and the rest of society, makes democracy a juicier prize. So so this enlarges the range of the parameter space under which the elite are forced to give up power and extend democracy. This is something they're never going to want to do. Okay, and this way of evaluating the problem in terms of political risk is, to the best of my knowledge, new in this paper. Okay, that's the idea. So this paper presents a model of trade policy under dictatorship and democracy. It endogenizes the threat of revolution to the occurrence of world price shock. This is a new step in this literature which typically treats the threat of revolution as exogenous. It also demonstrates formally when a dictatorship will choose not to install domestic, more efficient domestic redistributive fiscal capacity. One direction for future research is, of course, to take the model to the data. You can see I'm enthusiastic about doing that. And another direction is explore the circumstances under which elites deliberately choose inefficient redistribution mechanisms. So we're used to, trade policy is a very widely known mechanism. But we also see, it's a common feature. You talk to anyone from the IMF, they fly into these countries and they're like, this is so complicated. These measures that you have are so complicated. Why? Here we have an answer. Because you actually want inefficiency if you're a dictatorship. This shrinks the range of the parameter space where if you face the threat of revolution, you have to give up power. Yes.
You have explained, I think, if I followed you, that if it's a small country, not
Yes.
China,
Yes.
then you can substitute domestic by trade. You can substitute domestic taxation by trade and do things by just controlling the trade policy. Have you given a thought to what China would do?
Yes, that's a terrific question. The one complexity that you introduce when you introduce a large country is the terms of trade. So when you're a large country, the way that, in addition to the redistributive motive that you introduce for trade policy, you also introduce what's called the terms of trade motive. And the terms of trade motive can make the whole nation better off or worse off. Okay? You restrict, if you're an exporter, if you're China and you've got rare earths and you restrict exports of rare earths, you increase the price of rare earths. This might be something that makes everybody better off. So even though you're redistributing towards the elite with this policy, you may make the poor better off by enough that they're like, yeah, okay, through that mechanism, we'll take it. We'll take the status quo. So however, those sorts of things are well known. So, to focus on the Acemoglu-Robinson sort of parallel, we set those considerations aside in this framework. Yes, but it certainly comes into play and could be modeled. Yes.
So I echo Pradeep's observation, which I interpret your answer as saying that large countries actually have much greater ability to maintain dictatorship. But I want to. You can dispute that.
No, that's not what I'm. That's not what I'm saying.
Very good. I tell you what. I'll give you a chance to dispute that.
Yes.
Let me ask another question. In part of your introductory comments, you suggested that we may actually be moving towards more dictatorships.
Yes.
Is there anything in your mechanism that would enable a movement away from democracy in countries?
Yes, thank you.
You can refute the first comment. And
yes,
then...
two terrific questions. So, the key. Let me take the second question first. I mean, the key thing here is really that makes dictatorships' behavior different from a regular politician is facing the threat of revolution. So this is very costly to them, and it's something they want to avoid. You get out of power, you're not really you lose power, okay, that's costly, you don't enjoy the kind of rents from power, but it's not the same as really facing the threat of a revolution. So that's the sort of core mechanism. So to apply this logic directly, you'd want to argue that in moving from democracy to dictatorship, there's a personal cost to key agents within society. And I do think it could be done, but it doesn't follow as naturally. The thing that makes this interesting and not follow immediately the claim about, how is this going to affect different groups, is that what makes all of this interesting is the relationship, who owns what factor, and what good the country has a comparative advantage in. So the historical example is interesting here. In England and Prussia were very similar structurally in the 19th century. England and Prussia both had powerful royal families. They both had ruling elites, aristocracies that made money from land. However, Prussia had a comparative advantage in wheat. They exported wheat. England had a comparative advantage in manufactures. They're the first country into the Industrial Revolution. So the ruling elite in England wanted protection. They wanted high tariffs. The ruling elite in Prussia wanted free trade. They wanted complete openness. And vice versa. The poor in England wanted free trade. They wanted to be able to gain imports of cheap food. The poor in Prussia wanted closedness. They wanted export taxes that prevented the food from leaving to chase higher prices abroad. So this tells you can't just look for one constellation. You can't look for one ruling elite that are going to do well out of globalization and not like protection. The constellation is going to depend on who owns what and what comparative advantage the country has. Then once you map that out, then it becomes predictable. But saying things like, tariffs are always going to work because of X, or sanctions are always going to work because of Y, no. You need to know what the parameterization of the economy is.